Yeah. Anyway, we'll carry on what we are going to talk about today. So yesterday we start from the more electric aircraft, and then talk about the change of or the impact of this more electric aircraft concept to the aircraft electrical systems, and then we talk a little bit about the smart grid. For DC smart grid especially, and then we found the smart grid and the more electric aircraft electrical system, they merged in a kind of single bus DC common single DC bus concept. So common DC bus or single bus for aircraft application based on DC. Very much reflect the smart grid, especially DC smart grid. From there, we introduce a little bit about the droop control, because the smart grid, especially the DC smart grid, the droop control is kind of very good way to do the primary control in this hierarchical architecture. So we got primary control. Sorry, we got just quick reflect what we covered yesterday. Doesn't work. Okay, here we go. Yes. So yesterday we covered this diagram. We have for the this hierarchical smart grid control, you have the inner loop, which I think we covered a little bit detail today, and then you got primary control. Primary control, which I'm talking about, is the droop control concept, which mainly for implement this power sharing. Okay, and then secondary control is mainly to make sure that to eliminate the DC voltage deviation, okay, caused by this primary control due to the cable resistance or the measurement errors, okay, in the sensors. This is the secondary control responsible for. And then tertiary control is mainly the control which between the different grades and then do the power management. Okay, so this is what we learned yesterday in this smart grid side. So today we, come back again, to see how we use this smart grid concept in this aircraft electrical system side, and especially using the droop control, and also later on we look into a little bit about the stability issues of this concept. Okay. Okay, so this is we're going to, this is what we covered so far. So essentially, this is what we're going to talk about today. So the first one is the electrical power system generation system we developed in Nottingham University, which is we introduced about inner loop control, and afterwards we introduced we'll see a different droop control concepts used for this electrical power system. Okay, and for us, we only focus on these two levels, which means we only focus on this inner loop level and primary level. Okay, today, and to look at what's really this means to us. Okay. Okay, so just remind you again of this single bus concept we introduced yesterday. So I have three different sources, and this actually will in the future, later on, you'll see it. We have test rig exactly follow the same structure. Okay, so for this each source is essentially a kind of electrical generator plus AC/DC converter, and then of course we have the cables, connecting the source to the main DC bus here. Okay, so we start from give you kind of idea about this system we call AGUT, AGAS essentially is the project we did in Clean Sky, European Union project, which is quite successful. I'll probably talk a little bit more about here. For some of you probably haven't got any machine control backgrounds, I think it's good to give you some very brief taste of how we do this, how we control this machine, okay, using the part converters, okay. And just remind you again, sorry. Yeah, so it is multi-source system. So the generator 1 and generator 2, we represent the main engine-driven generators. And then the G3, we represent the generators driven by the AP, which is located at the tail of the aircraft, okay? The load-wise, later on, it will be a DC-DC converter, the DC chopper, and some resistive load bank as well. So this is the system we're going to talk a lot about today and tomorrow, okay? Just remind you the system, generators, power converter, cables, and DC bus, and some loads as well, okay? All right, so again, as we just focus on this a bit. So electrical generation system with droop control distribution, okay? So this is focused on the single generator system side, okay? So if you look at the machine and converter, what's really represent essentially is two AC source. So electric machine is one AC source. The power converter, which connects to the DC bus, essentially transform the DC power to the AC. So there will be another AC source here. So you change the voltage, the phase angle of the voltage, you will have the very nice power control of this between these two sources. Okay, so the power can flow either from the source from AVA to source A to source B, or from the source B to source A. It depends on the phase angle change. Okay. So we will replace these two AC sources with machines and power converter. This was the system will look like, and this was exactly what we have been doing in this AGAT project. So we developed the machines and we developed this converter, and at the same time we developed control as well. So by control this VC's phase angle, we can have the power flow either from the converter to the machine. We can use this machine to start the engine itself. That's why I call it a start generator. It's not only a generator, but also can run it as a motor to drive the engine itself. But today we mainly talk about this functionality, generation mode, which means the engine shaft driven the electric machine and then supply power to the load on the DC bus through this power converter. Okay. So this is a system we developed in Nottingham University. So this project is from 2011 to 2015, so about 4 years project. So in the project, Nottingham University, we developed this machine, design in electromechanical design, thermal design, mechanical design, and also the power converter. We designed the converter, we built out the converter, we test it, and then machine manufacturer tested in Nottingham University, and then we send it off to France for the test. So for machine-wise, we developed up to TRL 5 level, and then converter up to TRL 4 level. For the people who don't know what is TRL means, okay? So the TRL basically stands for the technology readiness, okay, level. So it's a way to reflect the readiness of a technology. So if you go to industry, you will hear a lot about the TRL, this kind of acronym. Okay, so if you look at from the bottom to top, tier 1 level, which means it's very low technology readiness, so which means something just concept idea. If up to 4 is something already in the lab, so it's some some technology being validated in the lab. So tier 4 to 5 is something about technology development. Even tier 6 level, which means you demonstrate your technology in a kind of platform which is similar to the one you're going to use in final product. So beyond 6 is more about maturity of this technology. So for university-wise, non-university, we can go up to tier 5 or 6 level, but beyond 6 is I don't think university can do it because more will be industry lead this kind of activities beyond this level. And tier 9, of course, for aircraft-wise, tier 9 means it's already in the aircraft. Okay, so for most of the research, if you go to universities, I think you did manifold between tier 1 to tier 5 level. Okay, for this typical project, AGAT project, we developed up to tier 5 level, which means we developed concept, we developed hardware, we tested, and we delivered to a customer and tested on their testing facilities. Okay. So this is the roadmap. You see the roadmap of this technology. Okay, the progression of good ideas, which means the how this technology readiness impacts on the the road mapping for the technologies. So if you see the tier 1 to 9, okay, so 1 to 2, it's about basic research. It's something very science-wise, put this way. And then afterwards will be 3 to 4 applied research. This I think what most of us are doing. Build up prototypes. And then from 5 to 7, it's more about from prototype you scale up to kind of full scale level. Okay. And afterwards is the system level development. Okay. You look at the involvement of people. So from 0, okay, so from 1 to 5 or 6 is academia, so like us, okay? Beyond this point will be more business, okay? Business get involved, okay? So small business will put interest in your research from the tier 2 level up to 7 level, okay? But large business, of course, beyond 7, so it will take over all the technologies, okay? The funding-wise, you see the government always sponsor up from 1 to to 7 level, and beyond beyond that, of course, they want the industry partners to lead all these research activities. Okay, and then for the private sector, they start from 2 to beyond 2 or 3 tier level. Okay. But there's one very interesting curve is here is this is called the value of depth. So all the technologies, all the concepts we developed in the university, is most of the time you end up here. Most of the time you end up tier 6 because 80% or even 90% of the technologies we develop in the lab, finish at this point cannot become products. For these particular projects, for AGAT projects, we are doing with the in the clean sky. Okay, we develop up to 5 level, and then we give it to a company in France, and then now it's beyond this point. So luckily this project is beyond this value of depth, and then become the commercializing product probably in 5 years' time. Okay. A little bit about the. Oops. So come back again. Talk a little bit about the the TRL thing. I don't know if any of you heard of this before. TRL level. No. It is something I think if you really do the industry projects, you know this a lot. So when I teach in University of Nottingham, student-wise, don't really have this kind of TRL thing. Even when I do my PhD in the university, only when I start to work with industry people, I got this kind of concept. I think for you guys, you guys are future engineers, in the world, put it this way. I think it's very important you get this kind of TRL concept in your mind, okay? I think this is not only about technology, but when you build industry, you should know where are we in terms of technology, okay? Anyway, come back to the point. So this is a system we developed in Northern University, and yeah, simple. If you draw this out, it's quite easy. You got machine, power converter, and then control. So the power-wise, is very important. Is for the system, rated power is 45 kilowatts. The machine size, like this size, and then this round. The machine can deliver, if you really push it hard, can deliver about 100 kilowatts of this machine. So if you got a chance to visit Nottingham, Alexandra, yourself, I think it's worthwhile to look at, because we still continuously test this machine at the minute in our lab. Okay, I'll show the lab activities for tomorrow. So we tested all in the motor mode. We tested in the generation mode. You see this droop curve. So you have the voltage and the current. So this is the voltage and this current. So the VO somewhere is 270 volts. So I have voltage change. You have the system supply power or current to the load. Okay. So this kind of droop concept, and this actually all the information I think you can see very clearly. So there are lots of dots on it, and actually it's from the experiment results. We just line this up and match with what exactly we want it to deliver. Exactly follow this droop characteristic. Okay, and then some quick recap again about this. Well, some parameters or the key numbers of these projects. Okay, so as this is 11 to 15, so it's about 4 or 5 years projects. It's within the it's called AGAS. Don't ask me what's the name of how we come to this kind of AGAS name. I have no idea. Don't ask me what's the really stand for. I have no idea either, because we like to use this small acronyms, and we have like loads of projects now. Like always use this acronym, and I have no idea afterwards. I have no idea what's really stand for. I just know the project, what's it doing, but you ask me what's this word stand for, I have no idea. So yeah, so essentially it is a start generator system for aircraft, and then we mainly focus on generation, because most of the time this system will be used as generator. Okay, so starting is very short period of 2 minutes, and then afterwards most of the time we'll be using it as generator. Okay, so the power density wise for the machine is about 3 kilowatts per kilogram. And the weight saving compared with the current technology in the aircraft is about 20% of weight saving, which is very, very significant. And this is why this project creates quite big impact in the whole EU. So if you look at the Clean Sky or Horizon 2020 projects, they always refer to these AGATS projects in terms of power rating, in terms of power density, kind of as a benchmark for any other projects now. Efficiency-wise, about 10% improvement compared with current technology in onboard aircraft. The current technology of this generation system in the aircraft, they're using kind of 3-stage generator. So you have 3 generators connecting in series, and then they have dials rotating with the shaft. So this is why it's not very efficient, and also weight saving, because it cannot rotate very fast, because the hydraulics rotating with the shaft, so you cannot really rotate very fast. In that case, you cannot have very high power density in the system. But for us, we can have very high power density, and then the efficiency-wise, we can move from the push the boundary from 80 they have got now to 90 to 92. Okay, so about 10% improvement of the efficiency. And also the new functionalities. I mean, for the conventional generators, they only can do generator. I mean, here you can do generation and motoring as well to crank the engine. So another one is, as I said, it creates a huge impact on this aerospace system. If you look at the technologies they're looking at in the aerospace industry, this start generator is kind of very key. Because the previous electrical machine can only do generation, but this one can do generation and motoring. So lots of projects are now actually what I'm leading is in this area as well. Okay. So this is converter, very briefly. So I think yesterday somebody, one student asked me what's the converter we're using. So actually, for aerospace application, we make it simple, okay? Either 2-level or 3-level at the minute. So the DC link on this side is, at that time when we do this project is 270 volts, and now we're looking at 540 volts at minute. So we use 3-level converter at that time based on IGBT, of course, based on silicon device, and mainly one consideration is the thermal consideration, because for 2-level converter, the losses in the converter is too high. For 3-level converter, you can bring down the losses. One of the challenges for this converter is because there is no, well, it's in the parabolic space in the aircraft. So the temperature, ambient temperature, we're looking at 80 degrees. Okay, not like 25 degrees we normally do in the industry. But in aerospace, its starting point is 85 or 80 degrees. And also, there is no liquid, so you forced you to do the air cooling. So what we do, we design this, the airflow from the bottom to top, and there will be 2 converters in this small parabolic cabin. And of course, we have to consider about the EMI issues. I think this is why something we need, as a parabolic guy, you always have to think about the EMI issues when you switch very high. And for aerospace application, you always forget about the liquid cooling, because there's no liquid available for you anyway in the aircraft. So always have to do the forced air cooling in the parabolics. I don't know if you guys do parabolic design. I think most of you probably do the parabolics, part converter design. One of the key things you really have to consider is the thermal management. Is very important. For silicon device, you always choose a device and then do thermal management, so thermal simulation. Normally we use Plex. I don't know if yesterday Gianpaolo asked you, guide you through this Plex software. So normally you can input the characteristic of the devices, and then you calculate losses with different operation points. And then based on these thermal losses, you can design your thermal management system. And then afterwards, you can, when you build the hardware, you're very comfortable to say, actually, your device is safe, because the silicon carbide device or any semiconductor devices, the core temperature of these devices is very, very important. For silicon devices, is the core temperature, but you are looking at 175 maximum. For the silicon carbide device, the core temperature you're looking at is about 225 degrees. So when you do the thermal analysis, you should be very much aware that when you do the parabolic design, your core temperature should have enough margin, or else very important. It's very easy that the parabolics will explode. Okay, I think yesterday I showed some students, what's really in the device. So anybody knows what's really inside this parabolics, this kind of module, this IGBT device? Anybody got any idea? No? Have you ever explored one of them and then start open it and look at it? So essentially, if a silicon device, you've got lots of different chips on inside. So it's called, what do you call this thing? A very small square. If you look at small squares and you got bounds, what's really happening is, if that temperature, this bounds is too high, essentially you destroy the devices. And we do explore a few of them, and then we did open it and see what's really going on inside. And you see actually it's become black essentially. I'll show you probably in the break. I'll show you some photos I've got for these devices, because I think for parabolics people, you should know what's really in that module. Okay, and I think that's quite important, and especially for power modules, because what we are doing not in university is quite high power. I mean, for this one is the power converter. We can drive power converter up to 60 kilowatts, it will really push the boundary. Okay. So this is the power converter, and then for the system, of course, you have to look at the control side. Okay, for the control this generation system. Essentially, for any machine control, I mean, especially when you talk about the vector control, the whole idea, the basic concept is to control an AC machine like a DC machine. Okay, so DC machine, everybody knows the back EMF equal to proportionate to the flux current IF and the flux, and also the armature current IA. So everybody know K equal to E equal to K omega whatever IF. If this is torque, is the motor is the torque equal to K multiply IF multiply IA. Okay, so the torque proportionate to the armature current, and then proportional to the flux current. The reason for that is because these two currents, if you draw in the vectors, they are 90-degree shift. So the armature current like this, and then the flux current like this, 90-degree shifts. And this idea for the vector control, exactly the concept is to align the voltage vector. So align the well, I can see that. So decouple essentially the AC motors. We're going to control AC motor as simple as control a DC motor. And what we are doing in this kind of mathematically, what we're doing for vector control is to decouple the current to be two components. One is called ID current, which control the flux. It's like IF in the DC motor. And then another one called IQ current, which is like armature current. Okay, so what we're doing is for this control of the machine, you have cascaded control loop. So the current control loop essentially, like we control the DC machine, we have the flux current, which is ID, and then the torque current, which is IQ. Okay. And afterwards, there will be flux victim controller. If this machine running very fast, you want to control this flux, so you have the flux controlling controller. To give the ID reference, which is the flux reference, and then for the power, which is referring to IQ, and also proportionate to the to IDC in the converter side. So you have the DC current controller, and to give you the IQ reference. Okay, so essentially you got ID come back to the DC controller, and then give you the IQ reference. And the droop itself is of course the out loop. So for this particular project, we're using the current mode control. So the reference, so the VI, this droop, give you the current reference. Okay, which we call the current mode control. The voltage feedback, of course, feedback to the give to the droop characteristic functionality, and then give you the IDC reference. Okay, so this is the control architecture. So we do apply the droop control for the generation systems. Okay, and for motor drives, of course, this current control loop is what I think most of you should be aware, and that's that the concept of controlling the AC machine using vector control is I want to control the AC machine like a DC machine. And the way to do it is I want to decouple the current to be, using a very interesting mathematical transformation, decouple this AC current to be like ID current and IQ current. And these two currents actually we call DQ axis. They change from ABC frame to DQ frame. What we have ID and IQ is kind of constant value. Okay, it's not sinusoidal. ID and IQ is always constant, and it's exactly like the DC motor. Okay, and then for the droop control, it is here. Okay, so we do have the droop control for for this generation system. Okay. Okay, so this is the hardware setup in Northern University. So this is I like to talk about this. It's very exciting. And this is our property actually, not university. So this test rig cost us about $500,000 test rig, so 500K pounds. So this test rig is, of course, prime mover, which is driving this machine here. So this very little one is our AGAT machine. Okay. So this prime mover is 150 kilowatts. So you can drive a motor to supply mechanical power up to 150 kilowatts. And the speed-wise, maximum speed for this prime mover is 35,000 RPM. Okay. Of course, it is an induction machine, so you see the huge. The machine is like this here, but you got lots of lubrication, this kind of system, a cooling system behind. So it's huge. It's huge. The whole room is probably like the size of the room, probably like this size of the stadium, and then the rig probably half of the stadium, will be like that size. So we test a lot. So this is we call it high-speed testing room in Northern University. So this is only one test rig. We have another two besides it. Okay. Of course, we test this one, and then the per converter itself is beyond the wall. So this is the machine room, and then the per converter will be in. So the controller or the students or researchers will not be in the high-speed room because it's very dangerous. So what will happen is the per converter and the control platform is beyond the wall. So we can see the window of the testing system, and then do the control ourselves. So this is the machine, and this is the per converter, as I talked about, and this is GSS. It's a DC, it's a 4-quadrant DC power supply, so it can be used as a load at the same time as a source. Okay. So in motor mode, when this machine as a motor, the power can transform from DC source to the machine. If it's generation mode, of course, the prime mover driving the generator and then supply power to the load, the GSS. And then we can change the voltage on the GSS. In that case, the current supplied here, the IDC current, will be following the droop concept. So if the voltage is 270 volts, there will be no current. If the voltage is below the VO 270, the current will flow to the load. But if the voltage is higher than 270 volts, which means it do regeneration, which means the power will power from GSS to the generation system. The current will flow into the per converter. Okay, so this is a kind of concept we use in the droop. So essentially, we manipulate the voltage here because it's only one system. We don't have multiple source on this test rig yet. So in the very beginning, we test this droop concept using a standalone system. Okay, so in that case, we just manipulate the voltage here to see if the droop really works in this standalone concept. And this is the results we got. Just scale up a bit. So yeah, so all these dots. So essentially, we set up the voltage and then see the current. So notice what's the voltage, what's current from the GSS. So we just draw the line. So essentially, this is the reference line in the red, or the dots. You see, it will follow this droop very, very well. Okay. So here is 270 volts. The reason why for 270 is for aerospace application. The 270 is a kind of standard. If you go to automotive industry, probably they'll tell you about 48 volts or 460 volts. Okay. So for aerospace, it's 270. So this is why when voltage is 270 volts, there will be no current. Okay. So when the voltage is below the 270, so the IDC is positive, which means the current flowing to the load. But if it's higher than 270, which means I'm doing the regeneration, which means the power, the current flowing to the from the load to the power converter or to the generator. Okay. So this is the droop concept we implemented. Standalone concept, and afterwards we developed this very beautiful system, use droop control concepts, and they will of course want to, as I said, in the future aircraft probably have multiple generator systems. This one I want to look at this multiple generation system with droop control consideration. Okay. Any questions before I move ahead? No? Good. Which means you get very clear about what I'm talking about. It's good. That's one. Okay. So for the droop concept, I think yesterday we discussed there are 4 kind of droops. So you can VI, VP, or IV, PV. So, but I said the power P is essentially the current. So in that case, we only focus on these 2 droops. Which one is voltage droop? So the multimodal droop, you got the voltage as reference. So you got V and I, and here you got I and V. Okay. So one is voltage droop, other one is current droop. So these are the 2 droop we're going to talk about. Okay. So for the droop, if we use this droop concept for our AGAR system, what's going to look like is that just this block. So all this. You look in the future, you find out all these are the same. All these are the same. I didn't change this at all. So there 2 PI is current loop. Yeah, as I said, this current loop is control the ID and IQ. So one is control the. So this control the flux. This one control the torque. Okay, or the active power. So this control the reactive power. This is active power. And for the for this. Voltage mode, what you really find out is current feedback. Yeah, the current feedback to the connect to the droop. So in this case, the voltage is as a reference, okay, to the DC voltage controller. Okay, so you see this is VDC. You have a local current feedback loop, okay, to the droop characteristic. So we connected this one. Simple. Yes, go on.
The control structure of the current component is different from the standard one, the active rectifier. Due to combination of the active.
You mean this one? No. You'll see later. So there are 2. Yeah. So you'll see. Oops. Yeah. There's another one here. Yeah. There are 2 types. I'm going to cover this one. No worries. Don't worry. So this one is the voltage droop. So what we're talking about is the current droop, current mode droop. There are 2. So yesterday, I think when I talk about mainly is the current based. Oh, so current mode droop. Yeah. Okay. So this is the you have one system, you have multiple systems. What you really have, you have these multiple generator systems like this. Okay. So every local current feedback to its own droop controller. Okay. So this is the concept. So you have the multiple generator system, and then you feedback all the local current to your droop block this way. Okay. And you have this different voltage reference supply to this the voltage reference, and afterwards, this control loop give you the V1 and V or V3 because for this system only 3 generators. Okay, and then this give you this kind of subsystem or this generator system control itself. Okay, so key concept here is we present this. How you can apply this droop to multiple systems, but essentially just feedback all this local current to its local droop. Okay. So actually, yes, this is actually what we're pretty familiar with yesterday. So what's this droop? The voltage mode droop is essentially you got like voltage connect to resistor, okay, virtual resistance. And what we talked about yesterday as well. So you have this concept, but the thing is, the main problem for this voltage mode droop is if you have this line impedance, okay. When I design the power sharing, I design the droop RD1, RD2, RD3. I want the power sharing exactly follow the I1, I2, I3 should be equal to 1 over RD1, 1 over RD2, and 1 over RD3. And the R1, R2, R3 should not be there because I don't know the impedance, line impedance in my primary control. But what we really end up with is actually, you have the line impedance in the power sharing equations. So here RD1, RD2, RD3, I change it to K1, K2, K3 to don't confuse yourself. So this K1, K2, K3 with droop gain, and this R1, R2, R3 will be the line impedance. Okay. So for another one, it's called local the voltage. It's called local voltage feedback. Essentially, in the current mode droop. So essentially, what you have, you feedback voltage to the droop. So the current reference will be generated from this droop gain. Okay. So for this current modes control, you got local. Well, I think it's sometimes very confusing. So current modes, there are two different types. One is the local voltage feedback, because the reference is current. Okay, so it's what I call current mode, but it needs the voltage feedback. So have local voltage feedback, which means the voltage, it is the I think I don't have. No, I don't have that one. If I go back a little bit. So what I mean, you can either feedback. I think one more step probably. Here we go. So you can either feedback the local voltage here to your droop, or you feedback this common DC bus to the droop. Okay, for this concept. So you end up this two different concepts. I think most of them, most of the literatures before is mainly use the local voltage feedback. So we propose, not in university, our colleague proposed kind of global voltage feedback. The beauty for this one is you can guarantee that you can always guarantee that your power sharing is exactly what you want. But there is some issue for this global voltage feedback. I'll talk about this later as well. Okay. So for this local voltage feedback or the current modes droop, what you really use is you can use current source to represent this droop. Okay. So we find out this current sources, the current essentially equal to the I1, I2, I3 equal to this. The reference VO is the open circuit voltage minus the feedback voltage over K1. Okay, so this K1 or K2, K3 is we call the droop gain. And for global voltage feedback, what you really have is you instead of have a local voltage here, you have a bus voltage, okay, common DC bus voltage. So either you feedback the local voltage to your droop gain, or you feedback the global DC bus to your droop gain, okay. So which means you either feedback this V1, V2, V3 to your droop, or you feedback this common DC bus VB to your droop. So what we end up with, I probably go through here. So for local voltage feedback, we find out, again, the same as we discussed yesterday. So with the cable impedance or resistance, you always have this in your power sharing equations. So this which means the line impedance, line resistance will have impact on your current sharing. So when you design your droop, you don't really have the, well, no, sometimes you don't really have the understanding of your knowledge of the cable. The length of the cable probably don't know when you design your system. But for the global voltage feedback, current modes, droop control, you get rid of this line impedance. The reason you get rid of it is essentially you have already considered about this line impedance when you design this droop game. Okay, so you find out this current sharing is exactly what you can design with. Okay. A quick summary here. So the methods, there's three methods. So one is voltage mode droop control, and the current mode droop control, which is using the local voltage feedback, and the current mode control using the current mode control using the global voltage feedback. So the actual sharing, you see the sharing accuracy. Only the global voltage feedback current mode droop control have the capabilities to have the accurate load sharing. The reason you do that is because you already consider about line impedance in your droop design. Okay, and these two methods, you do have the line impedance in this in your part sharing functionalities. Okay, and these properties I think is very important to look at. So for the voltage droop controls only depend on local measurements. Okay, and the same as this local voltage feedback current mode droop. Okay, because only depends on the local measurements. But for this global voltage feedback, you need an extra global voltage measurement. Okay, so this is something extra you have to pay for it. So this is good, sounds very good. But the main problem for this global voltage feedback is if it's global, which means if the DC common bus is very far away, okay, from your local from your local generation system, this will become very problematic. This is something probably needs to be, well, for aircraft application probably good, but for the land scale or smart grid, probably another story. So I think, again, because aerospace or aircraft is a very specific application, in that case, a global voltage feedback-based current mode droop control is kind of option for us to use. Okay. And there's some simulation study or experiments. I think it's a simulation study at that time. So you see that's part sharing. So essentially, for this three diagram, essentially, I want the ID to I3, well, three sources to be shared 2 by 2 by 1. Okay. So what's really happening is this IDC, ID2, ID3 on the voltage mode approach. When you have the line impedance, if essentially I want to be 2 to 1, but actually it's not. Okay, so it's 1.9 something to 1.9 something to 1. And then the second one, if you use the local voltage feedback, current mode control, again, roughly the same results you find out with the voltage mode approach. But if you use the global voltage feedback and then current mode droop, you find out actually exactly follow what I designed, okay, which is good. So in that case, somehow we're very happy with the results. This kind of global voltage feedback and does give you the capabilities to allow you to accurately do the part sharing between different sources. Okay. Okay, I think this is very quick summary actually. So half an hour. So essentially, the droop concept, it's a quick summary, is droop concept. For single bus application, we quickly discussed, and also the different droop techniques compared in terms of part sharing, especially, and then you find out global feedback, global voltage feedback. It is seems to be the most proper way, to allow you to do the accurate part sharing. Okay, even with because about line impedance. Okay, so this is just about 40 minutes Is it? Yeah. So, any questions? Yeah, I think this is for the first lecture. So, any questions? Yes.
About the global voltage feedback,
Mm-hmm.
it is possible that that kind of feedback produces more stability issues because of the
Stability issues. For this global voltage feedback.
yes, more than the local voltage feedback, or it is just the same?
You will see this later. We'll find out for the stability issue, the local voltage feedback and the current and global voltage feedback, they have roughly the same stability. Both diagram put this way. So you see, you don't really have for stability-wise, you don't really gain a lot. No. What's really gain in terms of for this for stability-wise, you have sources connecting parallel, and you have some gain, or you have some kind of benefit by connecting sources in parallel, a multiple sources system, which compared with single or standalone system, you have better safety margin or stability margin, put this way. But we talk about this local voltage feedback and global voltage feedback, there's no impact. This is the thing. So again, this was what I said. It's a compromise here. So what you gain is really just to have accurate power sharing, but for stability issues, you have no gain at all. No. Mm. Yes, exactly. So you find actually, if you go next lecture, later on, we'll talk about stability. So here, just give you a concept of what we're doing. Yes, I just totally agree with you. I mean, for the later on, you'll see for the voltage droop. Okay, so voltage mode droop, this system, this droop actually more like a feed-forward control. So you don't really, this droop gain have no impact on the stability. But with current mode, this droop gain actually is being included into the system. So you have some dynamics change when you have the droop. But for this voltage droop, no. Voltage droop is more like feed-forward control. You'll see this later on. Yeah, yeah. I think, of course, when you have more soft, you have more problem. More soft droop, you have more problem in the current mode. Yeah. Mm-hmm. Yeah, I mean, so this is what we've done actually. So it's one of students figure out. I mean, he did his work, and then he finished his PhD now. So what he has done at that time is, we use the cables. But what we want to do now is global feedback. What feedback? We use the CAN bus. So you digital thing. So in that case, you can have long transmission distance. But at that time, when he is doing his PhD, he hasn't got time to finish the CAN bus thing. So what's my project? My student, one of my students working on, is to continue his work, and then using the CAN bus to transmit the global voltage bus, the bus voltage essentially.
Have you ever considered to not measure the voltage in the bus bar, but estimate it with voltage?
We can talk about this. We can talk about this later. Yeah, that's a very good point. We're thinking to predict this thing, but we haven't got to that point yet. We did. I have discussion with my student, and he did mention this, but I haven't come to that point yet. And there's something probably we can do later on together. Yeah. So to what we did, prediction essentially. You really want to get rid of this sensor, but predict this bus voltage. A very good point. Yeah. Thanks.